Sophie wants this part too. Okay, we're on. So derivative of cosine is negative sine. I keep everything after that the same. But then once I write that down, I have to come back and take the derivative of the part that was after the trig function. And this requires the chain rule again, but it's just the normal chain rule where you pull the power out front, make it to the one less power, come back and take the derivative of the part that was in parentheses. So I like to kind of pick out all of the single pieces. That's like a -1, that's a 2, that's a -2. So -2 times -2 is 4. And since this part is not with a trig function, I'll put that next. And then sine of 1 minus 2x squared. I kind of like to put the trig function last. And that's basically it for 52. Again, I think we did one kind of like that yesterday. Now, I'm jumping here to number 54. And I think in the book they gave it to you as secant of 1/2 theta, tangent of 1/2 theta. You can think of that as theta over 2 if you like that better. It really doesn't matter though. If I look at what they've given me, and they're using theta instead of x's, but it's something with theta times something with theta. This is going to at least start out with the product rule. So 1 is the part with secant, 2 is the part with tangent. So here we go. This looks weird, but this is g prime of theta, and it is 1, which is secant of 1/2 theta, d2, coming back to my derivative of tangent, which I am going to have to do the chain rule with, but just the derivative of tangent is secant squared. So, like I did right here, take the derivative of the trig function, leave everything after that the same, but what am I going to have to put right after that? 1/2, because that was the derivative of the part after the trig function. If you want to change the thetas to x's, just temporarily, you can if that is kind of confusing. So 1d2 plus 2, which is tangent of 1/2 theta, d1. And I don't think I left enough room here because the derivative of secant is secant tangent. So I'm going to have to put right after that secant of 1/2 theta. I'm going to just add to the list here tangent of 1/2 theta. But again, you'll have to come back and take the derivative of the part after the trig function. So that's a 1/2 down there too. Now, I probably do have some stuff in common that I could pull out front. This is the plus sign here, so I'm looking at this stuff and I'm looking at that stuff. They both have a 1/2, so I may go ahead and pull that 1/2 out front. Now, anybody see anything else that they have in common? A secant of 1/2 theta, let's go ahead and pull that out front too. So I'm just going to cross this out real quick. That is gone, that is gone. Now, for this part, I just have secant squared of 1/2 theta. Okay, in the back, secant of 1/2 theta is gone, 1/2 is gone, and I'm going to go ahead and make that a tangent squared of 1/2 theta. There's really nothing else that we could do with that. I don't think there's any other identities to apply. So that would be it for 54. Okay, questions about either of those? I don't remember which one's next. It's 58. So let me maybe give you the answer to 56 first. On 56, I would rewrite it, kind of like the one we had in the notes. Pull the cosecant up top so it becomes sine. And I think they were using v here instead of x. Doesn't really matter. So once I rewrite it, it says cosine of v times sine of v. And then to do that, it's just the product rule. You could do the quotient rule, but I think it gets a little messy. So if you did it the way we did it in the notes, it should be cosine squared of v minus, not times, minus sine squared of v. My v's kind of look like u, so it's possible it could have been u. I don't know, u or v. Either way, for your variable on 56. Okay, 58 is up here. And again, they're using a different variable, so if you want to change it to x temporarily, you can. I would probably rewrite that first. Now, when I rewrite this, the cosine of pi t is being squared, but the 5 is not being squared. So I would actually kind of keep that 5 out front and maybe rewrite it as 5 times cosine of pi t squared. And to start my derivative, this is going to be kind of like the chain rule in the chain rule. I'm going to have to start by pulling my power out front. And so I would take that 5 times the 2 and make it a 10. Make my new power 1 less, so now that's to the first power. But then I have to come back and take the derivative of the part in the parentheses. And at this point, now we're using the chain rule for trig functions. It started out just the normal chain rule, but here it is with trig functions. The derivative of cosine is negative sine. So I do that and I leave everything after it the same. But then I have to come back and take the derivative of the part that was after the trig function. So what is the derivative of pi t? Just pi. Yeah, remember pi is just a number. So to simplify it, I've got a 10, a negative, and a pi that I could pull out front. So that'll very nicely become a negative 10 pi. And after that, everything else is getting multiplied. It doesn't really matter what order you put all this in. I just am going to leave it with the cosine of pi t and then the sine of pi t. You can't really factor anything out anyway. It's not like it's a sum or a difference. It's just everything multiplied together. Okay. Number 60, I think, is actually pretty similar. I'll just run through this real quick. I would rewrite it as, I probably don't, yeah, I might as well. I'm going to rewrite it as cosine of 8 pi, not pi, theta, all of that squared. It's the same as what I did right there. It's just I don't have an extra number out front. It's just the whole thing squared. So pull the 2 out front, make it to the 1 less power, and coming back to take the derivative of the part in the parentheses. Here we go again. Derivative of cosine is negative sine. Keep the 8 theta the same, but then derivative of 8 theta is 8. So 2 times a negative times an 8, that would make a negative 16 out front. And again, order doesn't really matter too much. You'll have a cosine of 8 theta times a sine of 8 theta. So 58 and 60 are pretty similar. Questions about those? All right, we're going through a lot here. If you go to number 62, it's actually pretty similar to 58. I would rewrite it kind of like this first. You'll have a 2 out front and then cotangent of pi t plus 2, and you pretty well have to follow the same steps. You pull the power out front, make it to the 1 less, come back and take the derivative of the part with cotangent, using that. I think final answer on 62 is negative 4 pi, cotangent of pi t plus 2, cosecant squared of pi t plus 2. The cosecant squared came into play just because that's the derivative of cotangent. Alrighty, any other problems? Yes. 51. I'll go ahead and put it up here. I think we're probably good at least with that. So 51, it says y equals sine of pi x squared. This is a good one because it's not like that where the entire sine of pi x is being squared. The only thing being squared here is just pi x, not the part with sine. So we're not going to do it the same way we did 58 and 60. I would just start out using the chain rule for trig functions. The derivative of sine is cosine. Leave everything the same after that, but then come back and take the derivative of the part after the trig function. And this actually also kind of requires the chain rule. It's a quantity with x's raised to a power. So pull the power out front, make your quantity to the 1 less, and then come back and take the derivative of the part in the parentheses, which would just be pi. So to write this out, I think maybe on 51 I actually called it pi squared. I'm not sure what the book did, but you can multiply all those things together. So I did a 2 pi squared x out front, and then just cosine of pi x squared. So a little bit different on 51. Good question. Yes?
You said the answer was 62.
Yep, 62. There's a negative 4 pi, and then cotangent of pi t plus 2, cosecant squared of pi t plus 2. You need me to go through that one?
Yes.
Yes? Okay, sure, I can. 62, coming back here. It is like 58 and 60, but a little bit different since our derivative has a square. So 2, I didn't put h of t out front. Darn it, I probably should. H of t equals 2 cotangent squared of pi t plus 2. Pi t. I feel like I'm saying potty. Pi t plus 2. Okay, so I probably want to rewrite this first, kind of like this one. The only thing being squared is the cotangent of pi t plus 2. So keep the 2 out front, kind of like we did with that 5. And now the entire cotangent of pi t plus 2 is being squared. That looks a little bit better. So here we go. Derivative. Starting with the basic chain rule. It's a quantity raised to a power. So I start by pulling the power out front. 2 times 2 gives me the 4. Make your quantity to the 1 less power. So now that's just to the first. But then we go back and take the derivative of the part in parentheses. So here comes chain rule for trig functions. Derivative of cotangent is negative cosecant squared, not x though, for us it's pi t plus 2. And then I have to come back and take the derivative of the part that was in these parentheses, which would just be pi. So this is your negative 4 pi that was out front, negative 4 pi, and then I'm just going to put cotangent of pi t plus 2, cosecant squared of pi t plus 2. All of that multiplied together. Okay, anybody else? Good questions, yes? 61, okie doke. Let me put this maybe on the side in case anybody needs this. Does anybody need 62 still? Okay, I'll just put it back here then, might as well. 61, and it says f of theta, so that's a little different, of 1/4 sine squared of 2 theta. I would rewrite this, keeping the 1/4 out front, rewrite it as 1/4 times sine of 2 theta, that whole thing squared. The 1/4 isn't squared, just that part is. So, pull my power out front. I'm starting the derivative now. 2 times 1/4 would be 2/4, but I'm going to simplify that. Make my new power 1 less. So now it's just to the first power. Come back and take the derivative of the part in the parentheses. Here's the chain rule for trig functions. Derivative of sine is cosine. So there's that. But I have to also take the derivative of the part that was in these parentheses. And derivative of 2 theta would just be 2. Now this actually works out kind of nice because 1/2 times 2 is just 1. And I've got other stuff, so I don't really need to put the 1. I'm just going to do sine of 2 theta, cosine of 2 theta. Okie doke. Did that help on that one?
Yeah, the back of the book just simplified it really well.
Okay, yeah, I would just leave it like this. They may have done something fancy on that one. Yes?
Number 53.
53, all right. You guys are working me hard today, but this is good. On 53, I like this one. It probably requires the product rule. This is 53 here. H of x equals sine of 2x cosine of 2x. If you didn't have your homework done today, you're in luck. We've been doing quite a few of them. So how do I know that I need the product rule? I have something with x times something with x. You got to be on the lookout for what rule you're going to start with. So this is 1 and this is 2. And here I go. 1, which is just sine of 2x, d2. So to take the derivative of cosine of 2x, I start by taking the derivative of cosine, which is negative sine. Leave everything after that the same, but don't forget to go back and take the derivative of the part after the trig function. So this is 1 d2 plus 2 d1. Derivative of sine is cosine, but again, I have to also take the derivative of the 2x, which is just 2. So, what do I have here? I'm going to maybe just show a couple steps. There's a negative 2 that I would maybe pull out front, and you could actually write this as sine squared of 2x since there's 2 of them. And then back here, leave that 2 out front. You could write that as cosine squared of 2x. I guess the only thing that you could maybe pull out front is either a 2 or a negative 2. If you did the -2, that would change to minus cosine squared of 2x. Not really going to get us very far, though, if we pull something out front. 53, yes?
Do you know why in the back of the book, like, they had, like, 2 cosine of 4x?
2 cosine of 4x. They probably used like a double angle formula from trig. Since these are both 2 x's here, they probably did something fancy like that. So, yep, don't worry about that. We'll just leave it the way it is. Anybody else? I don't even know which ones we haven't done yet, but that's good. Ask as many questions as you need to, because like I said, this is one of the more complicated things that we do with derivatives. Now I'll just go back to that here. We are going to finish 2-4 today. I know we spent a lot of time on homework, but you'll find that this part 4 is easier than part 3. So we're not going to have as much to do, I don't think, today as we did yesterday. Okie doke. My plan is on Monday, supposedly we're going to have a Veterans Day program, maybe 3rd period. I haven't heard much about it. So we'll go over our homework, and that's probably about it on Monday. I'm not sure how much time we'll have. And then quiz won't be until Tuesday. I've got it over there. Binders will be due Tuesday as well. I'll look up which assignments that'll be. But anyway, that's just coming up soon, so don't forget. Now I'm going to give you, there we go, I'm going to give you a couple more derivatives to add to your list today. Not trig though, thank goodness. We're starting with derivatives of exponential functions. And we've actually already done one of these. So, little bit of review here. Let me start with the one that we already know. If you have e to the x, so this is just your function, e to the x, we already know that the derivative of e to the x is e to the x. Probably the easiest one to remember. Okay, now what we're going to get into today is kind of chain rule-ish, and it's not just going to be e to the x power that you're given. You're going to have what we call e to the u power. And the u is basically just some function of x. So in other words, it's not x, it's 2x, or 5x minus 4, or maybe it's x squared. It's something with x, but not just x. If that is what you have with your function, to take the derivative of that, it starts out kind of like what we know with e to the x. It starts out just what you were given, e to the u power, but then you have to multiply by the derivative of u. So again, it's chain rule-ish in that you write down what you started with, come back, and take the derivative of that exponent, whatever was up there with x. Okay, so directions actually for all day today are going to be just to find the derivative, like usual. And I think you'll find that these work out pretty nicely. Okay, first one, f of x equals e to the 2x minus 1 power. E to the 2x minus 1. It's not e to the x, it's e to the 2x minus 1. A little bit different. So when I go to find the derivative, remember the formula said you start out with exactly what you started with. So the very first thing I'll do is basically just recopy what they gave me. But then I have to come back And I know the formula put a little dot. I think I'd rather just use parentheses to show that I'm multiplying. But go back and take the derivative of the part that was your exponent, the part that had x. So what is the derivative of 2x minus 1? 2. And really the only way to simplify that is just to pull the 2 out front. So derivative is just 2e to the 2x minus 1. Okay, not too bad. Not nearly as bad as what we had yesterday. Now let's try just a couple more, and we're also going to talk about some natural log derivatives today. But example 2 says f of x equals e to the x squared. It's not e to the x squared. It's really just e to the x squared. The only thing being squared up there is just the x. But either way, I'm still taking the derivative of e to something other than x. It's not just x here, it's x squared. So like last time, I start out by just recopying what they gave me, and then I come back and take the derivative of that function of x. And derivative of x squared is just 2x. So all I would do here is pull that 2x out front. So final answer is just 2x e to the x squared. Okay, now every once in a while you'll come across a function where there's maybe a little bit more going on. It's not just e to a power. Example 3 has f of x equals x squared e to the negative 5x. X squared e to the negative 5x. At some point, I am going to have to use my little derivative rule for exponential functions, but anybody know what rule I actually need to start out with? Product rule. Something with x times something with x. So let's do that, and then while we're doing that, we'll probably have to do what we've been doing on the others. 1 is just x squared. D2, it starts out with just exactly what they gave you, but then don't forget to go back and take the derivative of that exponent. So right now we have 1 D2 plus 2 D1. Derivative of x squared is 2x. Now, let me kind of simplify this as much as I can. We don't like negative exponents, so I know right here, I'm going to pull e to the positive 5x on bottom, so it's positive and not negative. And I also have a negative 5x squared that I would need to leave on top. The only thing you pull to the bottom is the part with the negative exponent. Now, same kind of thing back here. I'm going to pull that to the bottom, and I'll leave the 2x on top. So we're actually adding fractions with the same denominator. So why don't we go ahead and just make it one single fraction? It's like when you take 1/5 plus 2/5, keep the 5 on bottom, add your numerators. Same idea here. Keep e to the 5x on bottom, and I really can't add my numerators since they have different powers, so I would just leave it like that. I guess one other thing you could do, on top they have an x in common. I maybe wouldn't worry too much about that because it's not going to cancel with anything on bottom anyway. So either one of those answers would be fine. Okay, every once in a while the e part shows up maybe inside of the product rule, could even be inside of a quotient rule. Any questions about those? Not bad. Now, the last thing we're going to talk about are some natural log derivatives. And again, I'm going to tell you what the derivatives actually are, and then we will use them. Okay, let me just start with the plain old natural log of x. If you have just plain old natural log of x, the derivative of that is 1 over x. The derivative of natural log of x is 1 over x. Thinking about your quiz on Tuesday, you can have a half cheat sheet one-sided. I'd probably want these on there. I'd probably want my trig derivatives on there. There's a lot of stuff to think about. Now, one thing we do kind of need to think about with this is that, first of all, you never want the bottom of a fraction to be 0. So I definitely don't want x to be 0. And remember, you can't take the natural log of a negative. So to exclude 0 and negatives, we are just going to throw this little condition on that says x has to be greater than 0. It's not something you'll really write out every time. It's just something you kind of have to say. And you don't have to copy this down, but this is another reason why x needs to be greater than 0. This is just the graph of a natural log function, and the x's are all greater than 0. Okay, now what if you have a natural log of not just x, but something other than x? So in this case, we're writing it as natural log of u. Well, it starts out kind of like this. The derivative is going to be 1 over u, whatever was the function of x part. But you also have to multiply by the derivative of u. U prime is just saying the derivative of the part that was with the natural log. Okie doke. So we're going to try a few examples with natural logs. You might also remember our properties for logarithms from actually back to Algebra 2 and Pre-Calc. We'll have some of those properties show up along the way. But let's go ahead and start with this one. Number 4, f of x equals natural log of x squared minus 1. Natural log of x squared minus 1. It's the natural log of something other than x. It's x squared minus 1. So following that derivative for the u part, the derivative starts out with 1 over u. U for us is the x squared minus 1. But then I have to come back and take the derivative of u. So what's the derivative of x squared minus 1? 2x. And the only thing I would do to make that look better is to probably just put the 2x on top. Please don't try to cancel out an x. You would only be able to do that if this also had an x, but that's not the case. So I would just leave that the way it is. Okay. I'm going to keep rolling here. So, example 5. What do we have? Y equals the entire natural log of x squared. The entire natural log of x squared. If this was just that, natural log of just x squared, I would start out by putting 1 over x squared and then multiplying by the derivative of x squared, which is just 2x, and then I would simplify. But this is different because the entire natural log of x is being squared. So, because we have a quantity with x's raised to a power, we need to use our chain rule. I'm going to pull the power out front, make it to the 1 less power. I don't really need to put the 1 there, but there it is. And then come back and take the derivative of the part in the parentheses. So what is the derivative of natural log of x? 1 over x. And so I would probably just leave that x, this x, on bottom, and then that stuff can just go on top. Again, you can't cancel those x's out because that x is with the natural log and the other one wasn't. Okie doke. Now, just got a few more, so hang with me here. Example 6. This is where we might have to remember some of our log properties. It says f of x equals natural log of x times the square root of x squared plus 4. Back in Algebra 2 and in pre-calc, we had a property that said if you take the natural log of a product, you can basically separate that product by taking the natural log of each part separately. But anybody remember what I need to put in the middle? For the product property, it was always a plus sign. I'm going to start out by doing that. Now, even better than that, I probably need to rewrite the square root as a 1/2 power. I don't even know how I'm going to do the derivative yet, but I know anytime I have a radical, it helps to write it to a rational exponent. So taking the derivative, this is just a sum. So you can just take the derivative of each part separately. So derivative of natural log of x is just 1 over x. And then coming back here, this is the natural log of something other than x. So this is kind of like your natural log of u. That whole thing right here is the u part. So I'm going to start out by, actually, there's 2 different ways we could do this. I'm thinking of another property of logarithms. Anybody remember what we can do with a power? Yeah, that actually might be a little bit easier. If you want to use the power property too, the 1/2 can just stay out front. And now I'll start with this natural log of u business. I'm going to take 1 over u, which now the u is just x squared plus 4, times the derivative of u, which is 2x. Now, to make this look a little bit better, I'm going to write out a couple steps here. You can put the 2x on top, and on bottom you've got the 2 times the x squared plus 4. But I would go ahead and reduce that. You can sort of cross out a 2 on top and bottom. And I'm going to leave it as 1 over x plus x over x squared plus 4. That would be just fine. You could get common denominators to maybe combine those, but I don't think it'll look much better. Okay, product property, plus sign. I'm going to do one more example using our last property of logarithms, which is, I'm going to give it away here, the quotient property. F of x equals the natural log of 3x squared all over x minus 2. The quotient property says when you take the natural log of a quotient, you can take the natural log of each part separately, but what do we need in the middle this time? A minus sign. Yeah, quotient property always had a minus. So this again, I'm going to start the derivative here. This is the natural log of u. This is also natural log of u. We're going to take the derivative of each part separately. So starting out right here, I've got 1 over 3x squared. And derivative of that part right there, which was the u part, derivative of that is 6x. Minus, don't forget the minus sign, 1 over u back there would be just 1 over x minus 2. And technically, the derivative of the u in the back is just 1. So to make this look better, I've probably got a couple more things that I could do. The 6x is on top, but if you divide by 3 on top and bottom, you can make that just a 2 on top. And divide by x on top and bottom, you won't have an x on top anymore. That just simplifies to 2 over x minus 1 over x minus 2. Okay, be on the lookout for other properties. Now let me go ahead and write the assignment down. I'm going to put it over here. This is C42 from pages 168 to 169. We're doing 69 to 72, 84 to 93. On Monday, we will spend whatever time we have going over that assignment. If for some reason we're not in here at all on Monday, we'll still have time to go over this before the quiz. Keep in mind though, either way, we're planning on a quiz Tuesday along with binders. And I'm going to get those numbers to you right now. Binders are C28 to C42, the one that I just put up here. Binders are due on Tuesday, so keep that in mind. We only have a few minutes left.